On everybody, it's Mr. Gustin back in the chemistry classroom. Today we're talking about intermolecular forces. I'm here with Margie and Jesse. They're getting help, and I figured I'd make a video while I help them also. So let's talk about intermolecular forces. There are three kinds. We have London dispersion forces. We have dipole forces. And we have hydrogen bonds. Now, hydrogen bonds and dipole forces are pretty much, they're really similar in terms of what they do. They are attractions between polar molecules, but hydrogen bonds are molecules. But hydrogen bonds are between really polar molecules. So dipole is any polar molecule. Hydrogen bonds exist only between the polarist of molecules. And hydrogen bonds exist between molecules that have either O bonded to H, N bonded to H, or F bonded to H. And if you look at your periodic table, N, O, and F are in the same kind of section of the periodic table. That's because they're really electronegative or they're really non-metallic. They have strong nuclei and a few energy levels. So their protons really hang on to electrons. That's what makes these really polar, right? Positive hydrogen, a really negative or partially negative oxygen, nitrogen, and fluorine. Now, London dispersion forces exist everywhere. They are temporary dipoles. If these are dipole forces, these are more temporary. These exist between non-polar molecules. They actually exist in all molecules, but non-polar molecules don't have that partial positive, partial negative attraction. So they don't exist very well there. So if I'm looking for LDFs, I'm looking for non-polar molecules. If I'm going to see dipoles or hydrogen bonds, I'm looking for polar molecules. All right, let's look first at what I think the most famous polar molecule, water. If I draw water, it looks like this. Oxygen has two sets of electrons on it. It's a bent shape, so we know how to draw the Lewis structure. Hopefully we know then how to make its three-dimensional structure, and then hopefully we can analyze that a little bit. So if we're going to look at water as an example, let's figure out, is water polar or non-polar? I'm asking myself, is there a positive, negative side of this molecule, or is it kind of symmetric in its bonding? And some of you might say, about this axis, it is symmetric. The left side looks like the right side here. But while that's true, the top side doesn't look like the bottom side. The top side up here has electrons in it. That makes this side somewhat or partially negative. There are electrons up there. Oxygen is electronegative. It steals electrons or negative charges from hydrogen and stores them there. This means oxygen has partial negative. Now, secret, if you just look for the lone pairs, it tells you where the negative side of the molecule is. That makes this side of the molecule and this side of the molecule somewhat positive and somewhat positive. This is a polar molecule that will exhibit polar intermolecular forces. The question is it going to be a dipole interaction or a hydrogen bond interaction? In order to do this, we have to draw a second molecule because intermolecular forces exist between two molecules. Let's go ahead and draw hydrogen bonded to oxygen, bonded to hydrogen. This is my second water molecule. Let's label its partial negative, its partial positive sides of this molecule, and let's ask ourselves, whatever the attraction is between positive and negative sides of this molecule, is it going to be dipole or hydrogen bonding? Well, we know it's polar, so it's at least this. Let's check our H bonds. Is the bond of hydrogen-oxygen, is this bond between oxygen-hydrogen, nitrogen-hydrogen, or fluorine and hydrogen? If it is, that's a really big difference in charges. We're going to see a really strong attraction. So, is this bond between one of those three? Yeah, like it's between oxygen and hydrogen. That means this is super strong. This is the hydrogen bond. So if I wanted to label my IMFs, that's how I'd label it. Okay? Wonderful. Let's go try a few more examples. Let's go to the front board here. Let's try a few more. I'm going to change out my marker. Let's look at NH3. NH3, first things first, is it polar? Well, let's find a way to divide it so that it looks polar. If I divide it this way, it looks non-polar. It looks pretty symmetric. But if I divide it like this, I clearly see that there's an electron side or a partial negative side, and I see that there's a partial positive side down here. All of this down here is partially positive. So we start here. Writing this down. We start here. I'm going to go ahead and draw another NH3. While I'm doing that, I'm thinking to myself, this thing is polar. Let's figure out what the IMF present is. Clearly it's polar. It must be either dipole-dipole or hydrogen bonds. Well, I see that there is a hydrogen, so I need to check, is it hydrogen bonding? I see an attraction between this partial negative side and partial positive side right here, because this is negative and this whole here thing is positive. Let's see. Is hydrogen bonded to either O, N, or F? Yes. It is bonded to an N right here, right here, and right here. That means the difference in electronegativity is so large that we form a really strong intermolecular force, and we call this thing here a hydrogen bond. IMF present, it's really all of them, LDF, dipole, dipole, and H bond. But we're going to, H bond is just fine. We'll just call it the hydrogen bond for now. Why? Polar and hydrogen is bonded to nitrogen. Let's try another one. If I look at HCl, HCl is polar. How do I know? I can divide it right down the middle. Where are my electrons? They're on chlorine. Electrons mean this is negative. No electrons mean this is positive. Is it polar or non-polar? This has to be polar. Let's draw another HCl. Let's label its polarity. Partial positive, partial negative. We know that there is an attraction between the negative side and the positive side of a molecule. This is at least, because it's polar, going to be a dipole-dipole force. There's a hydrogen. Let's check if it's a hydrogen bond. Is hydrogen bonded to oxygen, nitrogen, or fluorine? No! It's bonded to chlorine, which means this is just a dipole-dipole force. That's what this is. We're going to try just one more. Just one more. Let's look at the top right. This is ethane. Can I divide ethane any way and make it asymmetric? I can't. Ethane is perfectly symmetric. No matter what, any one of those axes makes it symmetric. There is no partially negative side. There is no partially positive side to this molecule. This is a non-polar molecule. So I know that because it's non-polar, it's going to exhibit London dispersion forces, or LDFs. So some of you might say, how do I draw this? Well, you just kind of draw between two molecules. So you'll draw another ethane molecule. Hydrogen, hydrogen. And there's not really a net positive or net negative charge anywhere. These are really temporary dipoles. So we're kind of just going to draw some amount of attraction between opposite atoms in this molecule. And we can label these London dispersion forces. But these are very weak attractions. That's why most of these chemicals exist as gases at room temperature. So what have we covered? We covered different types of IMFs, different types including polar and non-polar molecules. We have London dispersion forces, we have dipole-dipole forces, and we have the strongest of the dipole-dipole forces, the hydrogen bond. How do we start? We start with our model and our shape. We then label our dipoles, our positive sides, our negative sides, and then we can figure out whether or not those attractions are hydrogen bonds, dipole attractions, or London dispersion forces. If you got questions, drop in the comments, send me an email, or as always, ask me in class. Till next time, see ya!